New phenomenon. If it has mobile electrons in it, and I take this bar of copper and I move it, just take it and move it through a magnetic field, and the magnetic field's pointing out of the board, what's going to happen to the copper? Which of these diagrams is going to best show the state of this copper bar? Think about the mobile charges inside the bar. They are moving with the bar, along with the entire bar, right? So think about what would happen to them in the presence of this magnetic field. Okay, we have a pretty sizable majority saying answer number 3, because if you think about the mobile charges inside the copper, we could, much like what we did with the Hall effect, we could just focus on the motion of, say, a single mobile charge, one of these, a single mobile electron inside this copper bar. Well, it's moving initially with the rest of the bar in this direction, but it's in the presence of a magnetic field. So what's going to happen to it? There's going to be, acting on the bar, a downward force, right? A magnetic force. V is that way, cross B. V cross B is up, but you multiply by negative charge, flips it. And so if you end up with these negative charges being deflected downward, essentially, then you're looking at essentially the entire electron C being shifted a little bit due to this magnetic force, and therefore you're going to have a buildup of negative charge on the bottom, a deficiency of electrons, and therefore a buildup of positive charge on the top. And when does it stop, or does it stop? You keep moving this at a constant speed, and this polarization occurs. Does it keep polarizing and polarizing and polarizing the longer you move it? What happens? Exactly. Just like the Hall effect, just like the velocity selector, we're going to get an electric force canceling out the magnetic force, right? So we have the magnetic force downward, but now we have, because of this polarization, an electric field. The electric field in here is pointing which direction? Down? And so if there's an electric field, that's going to exert a force on these negatively charged electrons that is up. Okay. And so we once again reach, well, it's not really a steady state in this case because there's no charge flow and there's no current here. But it's an equilibrium situation. It's a static equilibrium situation, even though we have a polarization, because the two forces are balanced out. Okay, and if you stop moving it, the magnetic field goes away, and then the polarization goes away as well. Okay. So that's kind of interesting, because just by moving something through a magnetic field, we can actually create a polarized metal and therefore an electric field. Let's just try in the other direction. Move in the opposite direction, what's going to be the polarization now? The electrons have mass, so how big of an effect is this? Or yeah. Well, the electrons are very light, right? Electrons are very light compared to the atomic cores, and in fact, I mean, you have, if you want to think about, let's go back to this first picture. You have a lattice of positively charged atomic cores where essentially almost all of the mass of the atom, that's where it lives, right, in the nucleus of the atom. And then kind of superimposed on this, you have these negatively charged electrons. There's going to be, in this case, when the bar is moving this way, there's going to be a downward force on the negatively charged electrons. There'd be an upward force of the same magnitude on the positively charged atomic cores, but these are very heavy compared to the electrons, right? So it's the electrons essentially that shift, and the positive cores hardly move at all. Okay, 10 seconds here. Okay, so we're going to get a polarization in the opposite direction, right? We haven't changed the direction of the magnetic field. We've just shifted the direction of the velocity. We're going to get a force in the opposite direction. V cross B is down, but QV cross B is up, multiplied by a negative charge. So we end up with negative charge buildup on the top, positive on the bottom, okay? Not surprising. What if, by the way, can we use this effect to tell the difference between positive holes or negative electrons as the mobile charges? What if the mobile charges were positive and the velocity was that way? What would you get for the polarization? Would it be different? V cross B is down times a positive charge, which doesn't flip the direction. We get the same polarization. So this effect doesn't tell the difference between sign of charge carrier like the Hall effect does. Okay, but it's still this polarization exists. Well, this is interesting, but maybe we can do something with this. Let's set up a situation where we have a bar of metal that is riding along. We're going to move it to the right, and it's riding along two metal rails. Okay, so it's in contact with these two pieces of metal, and it can slide easily. And between the two metals, we place a resistor. Okay? Think carefully. We've just created a situation where by moving this thing through a magnetic field, we're able to create a polarization. So see if you can make an analogy to something you may have seen before. Is there going to be any conventional current flowing through the circuit? And in fact, there is a loop here that's made, right? Because we're connecting this bar to these rails, to this resistor, so there is a loop. Are we going to get a current in this loop? And if so, what's the direction going to be? The thing to do is figure out the polarization first, and then see if you can make an analogy to a situation you've seen before. And we have, well, somewhat of a majority, 60-30, 61-35-2. Counterclockwise, and some people are saying 8 and 9 for some reason. Counterclockwise, let's see. If you have, first of all, what's going to be the polarization? What's going to happen at the top? What's going to happen at the bottom? What do we get at the top? Positive charges, right? Because V cross B, if the mobile charges were positive, they'd be forced upward. If the mobile charges were negative, they'd be forced downward. So you end up with that polarization. Well, what does that kind of look like? Where have we seen something like that before? Battery, yeah. If you could just redraw a circuit that looks similar to this, you have a positively charged battery here, a negatively charged terminal of the battery here, connected to a resistor. And in this case, conventional current is going to flow which way? Counterclockwise, right? Capital I comes out like that. Yeah, remember, conventional current comes out of the positive, goes in the negative. So, by the same reasoning, we should have a conventional current flowing that way. Let's look at the electric fields in here. We said that if you have a charge flowing, well, let's just look at the direction of the electric field. Electric field is going to be pointing downward, right? And the electric field here is pointing what direction? The electric field in the resistor is pointing what direction? Downward also, yeah, because the electric field in the rest of the circuit has got to point in the direction of the conventional current. It's driving the current. Well, wait a minute. The electric field here is pointing in the opposite direction of the conventional current. Can that happen? Yeah, right. First of all, the round trip potential difference has got to be 0, right? So the potential difference here is negative, and then when you go back here, the potential difference here is positive. And that's exactly what we have in the case of the battery, right? In here, the electric field is pointing that way. and the electric field in the battery is pointing from the positive to the negative. So imagine, just for the sake of argument, that the charge carriers are positive, just so we don't have to deal with the signs. Positive charge would be moving that way in the direction of the electric field, and then moving this way upward in the opposite direction of the electric field. So what in the battery, that's true. Here's V. What's supplying the force, or what's causing the electric field, or excuse me, the charges to move in the opposite direction of the electric field inside the battery? What was that called? Okay, that's the EMF, right? The EMF is the work done by, per unit charge, by something. Work by the, what do we call that, interaction? Anybody remember? Let me erase some of this. A non-Coulomb work, a non-Coulomb force, right, per unit, times the distance per unit charge. In the battery, that's provided by the non-Coulomb, meaning non-electric, okay, not due to static charges. In the battery, that's due to some chemical reaction. In here, what's that due to? What's driving the charges the opposite direction? The magnetic force, right? So the magnetic force is essentially playing the role of an EMF, and we could even figure out what it is, because we say that the magnetic force is equal to the electric force. QVB again is equal to Q times E. Cancel that out. And then if we knew the length of this bar, we could figure out that potential difference and say that delta V is E times L, or Q times V times, or excuse me, V times B times L. This is called motional EMF, because essentially the magnetic field is creating a polarization which can drive a current, just like an EMF or a battery can drive a current in a circuit. Okay, so by moving a bar in a magnetic field, we can create a polarization. Then we can actually get it to drive a current. And that's going to be useful for various technological applications, and we'll talk more about those next time.